Hello, everyone. Thanks for coming today. I'll be presenting on forensics. And yeah. So some announcements first. This Saturday, so it's Monday at 9 a.m., we're going to be competing in Sunshine CTF 2022. And this is going to be virtual only. There won't be an in-person thing because of the break. But we're going to have a few heavy hitters playing the CTF, and we would appreciate if everyone else could help participate. And we're trying to score high in the CTF so that way we can get a higher rating, potentially breaking top 50 in the CTF time ranking in the world. And as I mentioned, no meeting this Sunday or next Thursday and Sunday because of Thanksgiving break. So can you make all the challenges visible?
Well,
okay, they're forensics.
yeah.
Sorry, I don't think challenges are up yet, but we'll wait for them to come up. It's fine. You guys can remember this, right? I mean, guys, yeah, guess God. Or if not, you can just guess later. Okay, so what is digital forensics? I like to think about it in three different types. There's file forensics, file system forensics, and memory forensics. So file forensics is where you're given like an individual file and you have to either figure out the format of the file, what kind of data is encoded in it, and if there might be data hidden within the format. So that's what we call steganography. That's where we hide data inside other data. There's also file system forensics. So you're given a full file system, like a Linux root drive or a flash drive or something like that, and you have to usually you have to figure out what happened on the file system, either by looking at logs or by looking at other indicators of activity. And then you have memory forensics, which is unlike any of the other two because memory. Can you guys still hear mine? Okay, so memory forensics is where you're given, instead of a traditional file system, you're given a dump of RAM. And this is not like something that you could like necessarily like, there's no like concept of folders. It's just like the stack in your heap and and all your like program text in there as well. So memory dumps contain all that kind of information, and they're usually generated when your program crashes or something like that. So that way you can see what memory looked like when that program crashed. So first we're going to cover file forensics. And we'll cover some basic commands first. So this is the file command, which you can run on Linux. It will tell you what a file actually is based on the magic bytes. So every file format, whether it's PNG or JPEG or some sort of XML, they all have some sort of pattern to them that distinguishes a file format from a different one. So for example, PNG always starts with that hex sequence 8954E47. And you can find like a list of all these magic bytes or file signatures on like Wikipedia. But file uses those magic bytes, it references the database, and then it tells you what file type that file is. So don't always trust the extension because, for example, you could have a PNG file, but you renamed it with an extension of .zip, right? Usually like your Windows will try to open the file based on its extension, not by the magic byte content. So if you try to open that file in Windows, it's going to give an error because the PNG file is not a zip file. And here you can see we have file unknown.txt, but you can see the result, it says unknown.txt is a JPEG image data. So we know that unknown.txt is actually a JPEG file. And to use it, you just run file and then the file name. And then this is a real useful one when you're doing a file carving. This is binwalk, and it's kind of like file, except it tries to find magic bytes throughout the entire file. So it's like because some you can like append file types together. So for example, if you have a Linux binary, it might include a PNG within the binary, so that way it can display the PNG inside the program as a GUI or something. And so if you run binwalk on a file, it will try to extract, well, not extract, it will try to see all the file headers that match something that could potentially be a file. And then if you pass it the -e argument, it will take all those segments where they found a new file header and extract it. And so you can see here, I ran binwalk on cmd.exe, and it like tells you the offsets of all like these different things it found. But at first, it sees that it's a Microsoft executable. It also shows useful information like copyright string, because that might be useful for searching or looking up to determine the origin of a file. It also tells you like encrypted data, like it detected mcrypt encrypted data, or an XML document. And you can see it also detected PNG image, which is 256 by 256 pixels. And in that case, it's literally just the icon of cmd.exe. So you can basically extract all those files within the file by using the -e flag. And then strings is another very useful command when you're working with specifically binary files. So suppose you're given like a Linux executable, you can't just like cat that, because you're going to get a bunch of gibberish. Your terminal's going to break, and like there's all this ASCII nonsense going on. If you want to view just strings in the binary, you can use the strings command, and by default, it will try to find all strings of length 4 or greater and print them out. So that way you can see if there's any like strange plain text that might be there, something, any useful information from strings. And you can also change the length that you want to use. So strings-n16 will find all strings of length 16 that are printable and display them in the terminal. So here I run strings of length 16 and cmd.exe. You can see a bunch of kind of like function names, API calls, like this program can help you run in DOS mode error messages, things like that. And then there's XXD. So if all else fails, if you can't find strings, and you need to look at the hexadecimal representation, you can use XXD. It also can print out formats in like octal or other bases, but usually you're more interested in just the hexadecimal. And so you can see this is a hex dump of some random file. I don't know if this is from a previous slide, but you can try to find patterns in the hex code sometimes, because encryption kind of distorts stuff. So if you see a lot of repeating bytes of something, that might indicate that it was XORed by a single character or something like that. But XSD is just useful to print out hexadecimal information of a file. And then the last really, really useful one is grep. I'm sure you guys used this before, but you can just search for text within a file and recursively through files. So you use grep, which is you grep and then you put in the text you want to find, and then you put the file name. So if I do grep SIGPwny, and then I do, I don't know, a large file.txt, then it will show me all the instances, all the lines where it found the match for SIGPwny. And then grep-r is a recursive grep, so it will look through the entire directory for the text that you're looking for. And then you can combine this with other utilities by using bash piping. So you can first cat a file, and then you could grep for text. But usually you could just do this top part. A lot of people do this because it's a little bit more intuitive. When you're typing out commands, because you want to read a file and then cat and grep. I don't think there's performance issues, but it's fine. But this is probably the more useful case scenario where you're looking for text in a binary file. So you find strings, all the strings in the file, and then you grep those strings for the text you're looking for. Okay, and now we'll move on to steganography. It sucks, and here's why. You're hiding data and other data. It's inherently guessy during CTFs. You're going to try a lot of ideas, you're going to waste a lot of time, and you're not going to, if you do manage to get it, then you're a guess god, which is why the flag is guess god. But essentially, when you manipulate data to hide other data, it's going to change like the entropy or whatever of the original data. So you can use statistical approaches to find if something has been encoded with steganography.
That's my lowest point.
Yeah, this was sometime last year. I think it was for.
That was that was.
Wait, no, this is CSAW this year. That's right. Okay, yeah, right. Yeah, this is
absolutely insane. And that picture, I started trying to literally connect the dots. It was maybe my lowest point in all of CTF. All right.
Yeah, we were up to like 1 a.m. just. And so one very popular example of image steganography, where you're hiding data inside an image, is LSB, which is least significant bit encoding. And basically the way it works is, imagine you have your image, it has RGB values for each pixel. Each RGB is 1 byte. So if you basically take the least significant bit of that byte and change it to 0 or 1, depending on your message, then you can basically have a bunch of pixels and have a 0 or 1 in each pixel representing RGB. And then you can hide basically binary data in LSB. So then when you're decoding it, you basically take the last significant bit and then you concatenate them all together to form a binary message. And that can decode to whatever, like a file, text. Yeah. And because you're taking the least significant bit, you're taking the least significant bit, the image visually remains unchanged, right? You can't tell the difference because you're changing 1 bit on the least significant bit. It's like changing the hex color by 1 value. So here's a bit of a better representation of that. So you have like this pixel RGB 218, 150, 149. This is what it looks like in binary. And you basically change the original image so that way it's by default all zeros. And then you put 1s where you want to encode your message. So if I want to, let's say the original image was 001, but I wanted to encode the message like 111, I could change all these to 1. And then when I'm reading it back in, I just read back the last bit and I get 111. So can you spot the difference? Right? This is an original image and this is the LSB encoded image. There's absolutely no visual like differences that you could probably spot out. But if you use statistical analysis, so here, this is viewing only the least significant bit of red. Then you could see, like you can see, this is the shape of the guy, Mr. Incredible, and you can see that like it's all random except for the shape of his head because there's no like red values behind him. So you could like tell that this is like, it looks reasonable for a randomly like image with a lot of like background and noise. And here you could see it's a very constant pattern. And and this is because the flag was encoded repeatedly, but you could still probably spot like a large chunk of a pattern that clearly does not look random or matches the noise of the rest of the image. So there's a psychoanalysis tool. You don't need it to solve any of the challenges, but it's very useful for CTFs to do analysis for LSB. Other steganography, there's audio stego. 90% of the time it's a spectrogram. So if you view the spectrogram of the audio file, it'll show an image, which is kind of fun, but also kind of boring. And then other 10% is either SSTV, some frequency modulation, some random homebrew bullshit. It could also be Morse code, and then you just run it through a Morse code decoder. That's fine. And most audio stego can just be solved with tools and things like that. So this is for like reference if you want to look back later, but starting point, you want to first find out like what file you're dealing with. And you can use file or binwalk to do that. If you have image or video audio, it's likely to be steganography. If you have a document or some other like standard file format, there might be the possibility of hiding data inside that format as well. Like, did you know a docx file is actually just a zip file? So if you rename the extension to a .zip, you can open a Word document like a zip folder, and you could possibly hide data in it. If it's plain text ASCII, then what strings does it contain, and are there any patterns? And that's kind of similar as well for hexadecimal for a binary file, except you can use strings, or you can try your luck at looking at the hexadecimal representation and see if there's a pattern. And another thing that I didn't mention, but is kind of important, is metadata. So all file formats have a different way of showing metadata. For example, images will include location of the photo, camera model, and also like what kind of encoding it's using. And documents can sometimes include username of the creator and the directory where the file was initially saved. So for example, there was an attack where basically threat actors can like search on Google specifically for docx files from a specific like company website. And then they can find from the metadata of those docx files all the usernames and all their file directories. So they could probably generate a list of usernames to use in brute force attacks or things like that. And then everything else. There's a lot of different metadata types. File system forensics. So didn't really finish these slides that well, but it's all right. Logs. So logs contain information about what happened on the system. And if you read enough logs, you can create a trace of events that happen from, let's say, the start of an attack all the way to the end of an attack. And you can see exactly what an attacker does, because logs usually don't lie, except if an attacker is smart and covers up their tracks by modifying the log somehow. Except that's usually very difficult to do without leaving some sort of evidence. So on Linux, you can, as an example, I just put in some random log locations. But if I have a thing at the end of the slide called resources, and it contains a lot of different file system artifacts that you can look at to find useful information. In Windows, you usually view logs through Event Viewer because who likes text files? Windows doesn't. So with the file system, usually the way to give it to you is in these 3 different formats. You can get an archive or zip of the full or partial file system. So in this case, you're just working with the content of the file system. You're not worrying about disk shenanigans or file system formats, because you can just view the files in your own extracted file system. Another thing is that they might give it to you in the form of a disk image. So it's like a clone of the actual physical drive. And they give it to you as a single binary file. And this leads to some interesting things, because depending on the file system, let's say I delete a file, that doesn't necessarily mean the data for that file is deleted from the file system. So if you get a disk image, there's a possibility that there's some artifacts left behind that indicate a file was deleted, and you could possibly recover that deleted file. And usually you mount that drive as like a disk to your system. But also keep in mind that your OS might make changes. It might like write something to the drive that it mounts, and that might compromise the integrity of your analysis. So usually you use a tool like Autopsy or manual hex analysis to analyze file systems. And sometimes you're given live access to a system. So let's say I have like SSH access to a server. This is a little bit difficult to perform forensics on, because you can't guarantee the integrity of a volatile system. Like, it's constantly running. If you do something that affects logs, then like Yeah, and note that every second you spend not doing forensics on a system, like there could be some sort of service that clears the logs every 24 hours and you lose that evidence. So, and usually you don't want to turn off a system if you do have live access to it, because otherwise, depending on what is happening, the drive could be encrypted. So if I shut off the system and the drive is encrypted, when I turn it back on, I can't get back in. So live access to a system forensics, from the perspective of like real world professionals, is extremely difficult. But usually most of the time you're just looking through the files normally, for the purposes of CTF. And now memory forensics. So as I mentioned earlier, memory forensics is doing forensics on a RAM file. So instead of being given a traditional folder file structure, you're given the memory mapping that the memory that contains like stack, heap, program text. And dump files, as I mentioned, are usually created when a program crashes or your OS crashes. And they can contain really sensitive information because your program, when it runs, it has to store the secrets that's dealing with somewhere, right? And it stores it in memory. So if your program creates a dump, if your program is processing something sensitive, and for whatever reason your OS decides to create a memory dump because it crashes, then there's a potential for your secrets to be leaked in the memory as well. So for example, if you're like in the middle of viewing your password manager, right? At that very moment in memory, all your passwords are unencrypted because you've already unlocked and it's like decrypted it and it's loading passwords into memory. It could also contain your clipboard content, things like that. So memory forensics is very useful if we have a core dump file or a memory dump file, because we could find secrets that we normally wouldn't be able to access through a traditional file system. So there's a very special tool called Volatility, which can analyze memory dump files for you. It's a little bit quirky because it's got two different versions. Volatility 2.6 is technically out of, it's still being worked on, but like it's technically not, you're technically not supposed to use it anymore. But the thing is, the newer version, Volatility 3, doesn't have all the features of Volatility 2.6 yet. So there's kind of this weird in-between transition right now, kind of like with Python 2 and Python 3. As I said, Volatility 2.6 is older and it works great when it works, but it doesn't fully support new OSs because you have to recompile it every time. But there's a way to now add custom profiles and things like that. And Volatility 3 is completely rewritten. It's faster and it does work better with OS version and profiling, but you're likely not going to be able to extract as much data as you could when you're using Volatility 2.6 because it's just not fully feature-fledged yet. And annoyingly, you could have Volatility 3 2.4.1, which might confuse you with like Volatility 2, right? So here's a slide for setting volatility. You might need it for the last challenge, but basically you can install volatility, install the requirements. This is Volatility 3 specifically. And you can view, for example, the Windows process list. So I've given a memory dump that represents Windows at a time of a blue screen. And you can run things like viewing the process list of all the programs that were running at the time of the crash. And Volatility contains many other modules to find more useful information. Or instead of using Volatility and its complex tooling, you could just use basic commands. So you'll find that a lot of memory is literally just strings. So you could just strings it and grep stuff. And you could also just strings it into a text file and kind of just scroll through the text file and see if there's anything that's interesting. So you'll usually see like browser history just in the memory dump from strings. Okay, yeah, and that's it. So next this Saturday will be Sunshine CTF. As I mentioned, make sure to come out to that. It's virtual. And then because of fall break, we won't have a meeting this Thursday, Sunday, or next Thursday, or the following Sunday. So then we're going to start back with Pwn 2 with Kevin, and we're going to exploit format strings. And then Sunday after break, we're going to have another speaker from SPRY to talk about their security research. Thank you.